Number one, right? We are given a circuit and it has multiple switching events, okay? So that is the catch. That's the trick with this problem is you have a switch that goes from position A to B at t equals 0, and then from B to C at t equals 0.1. That means we're going to need two separate equations for IL, right? Because we're working with an inductor. As a result, we're looking for the current through it. So first things first, let's define the current that we're solving for. And I'm just going to choose it to be going down through the inductor. We can choose either direction. I'm going to choose down. All right, and that's going to be IL of t. So there's two equations we need to find. All right, we need to find IL of t for 0 less than t less than 0.1. It's actually less than or equal to. And then the second equation is going to be IL of t for t greater than 0.1. All right, those are the two equations that we need to find. But we have to look carefully at what the question's asking for. It's asking us to solve for I3 at those time intervals. However, we are going to use both of these equations for each of their respective time intervals to solve for I3. And I'll show you what exactly I mean by that here in a second. For now, let's just start with the basics, right? What we do know, and that is our initial condition, right? Step one is going to be to solve for IL of 0, or 0 minus, technically. So let's just draw the circuit with the switch in position A. Now, the problem tells us that the switch has been in position A for a long time, so we can write it to be in steady state, which means the inductor is going to become a short circuit. So I'm going to draw the circuit. Right, and this is the short circuit inductor. And since we defined our current for the inductor to be going down, we're also going to define this current IL of 0 to be going down. 10 ohms, 100 volts, 50 ohms, and 60 ohms. And just from looking at this circuit, what would IL of 0 be? No equations needed or anything like that. 10. Yes, exactly. Reason being is because this resistor and this resistor are both shorted out from this short circuit right here. Right, so IL of 0 is simply going to be 100 over 10. 100 volts over 10 ohms. So 10 amps.
Is there a different way other to approach that, like than Ohm's law? Because at first when I see it, I was kind of confused as to what to do first.
You could do KVL, but again, you're gonna have to, even if you did a KVL, you'd have to define a current through this resistor and recognize that this current is also IL of 0 because this current goes all the way down like that. So really Ohm's law is your best bet here. Okay, now for step 2, right? That's going to be find the final condition of IL of infinity. And that is after the switch flips, right? So we flip the switch to position B, and now we have to solve for the final value of the current. So I'm going to draw the circuit. I'm going to draw the inductor. Right, and then this is 60 ohms. And remember, since we're looking at the steady state condition when IL approaches infinity, or T approaches infinity, so the inductor is going to become a short circuit. And what's the value of IL infinity here?
0.
Yeah, exactly. There's no voltage source, no current source, no power source that can be inducing any sort of current in the circuit. So IL is going to slowly approach 0. Now we actually have a word for that. It's called natural response. Just terminology. Natural response is when you have an RC or an RL circuit that naturally decays to 0. A step response is when it decays to some non-zero value. Those are the two types of first order circuits that we work with. So this is a natural response. Now, one thing that a lot of people get confused with, in fact, so many people made this mistake when I took the exam last semester, is when you have multiple switching events, right? We know that the circuit is only going to be in position B for 0 less than t less than 0.1, right? It's only going to be at that position for that time interval. So obviously the current is never going to get anywhere near 0, right? Not enough time is going to pass for t to approach infinity. But that doesn't matter. You still need to find the value to be able to accurately model the current for that time interval. So suffice to say, you still have to find IL infinity, even though it's never going to get to that value. Because that's what we're going to need to build our equation, right? IL infinity plus IL minus IL of infinity e to the negative t over tau. We're still going to need IL infinity to build this equation so that we can represent IL of t for this time interval. So just a sidebar there. You always need to find your final condition. Now, step 3 is obviously find your time constant, which for inductors is L over R Thevenin. And so I'm going to replace the inductor with 2 terminals because we're finding R Thevenin as seen by the inductor. So we're going to remove it from the circuit and we're going to replace it with 2 terminals. And we're going to find the Thevenin or the equivalent resistance as seen by those 2 terminals, which very obviously is just 60. There's only one resistor, so it's going to be 60 ohms. Which means our tau is L over R. L is 6 henries over 60 ohms. So our time constant is 0.1 seconds. So our first equation for IL of t is going to be 10 amps e to the negative t over 0.1 seconds, because obviously IL of infinity is 0. So all we're left with is IL 0 times e to the negative t over tau. And this is our equation for this time interval. But remember what the question's asking for. It's not asking for IL, it's asking for I3. So let's redraw the circuit. And define the IL that we just found and I3 that we need to find. And what can we say about the relationship between IL and I3 here? Do they go the same direction or the opposite direction? Opposite, yeah.
So just negative IL.
Exactly. So I3 of t is going to equal to negative 10 amps E. And I'm going to do some simplifying here, all right, because 0.1, we have a decimal in the denominator, so we could change that to negative 10 inverse seconds t. For 0, oh, careful here, 0 less than t less than 0.1. And that is half of your answer.
Is I3 opposite of IL because it's like this like that?
Exactly, yeah.
Could you explain the last box, the ILT, where to do that?
Last box.
The very bottom left.
This one?
Yeah, could you clear what you did there?
Yeah, I just essentially redrew the circuit to identify the relationship between IL and I3, right? Because at this point, the switch is in position B.
Yeah.
So I'm just trying to look at this circuit for this time interval, 0 less than t less than 1, or 0.1, and looking to see how the currents relate.
And so, since I of t is 10 amps, I of t is just a negative.
Exactly, because that current's going to go like that, and that current's going to go like that.
Okay.
So they're going to go in opposite directions. So, yeah, okay. Now, this is where you start getting into circuits 2 territory, right, with the next step that's involved. So first, let me digress a little bit. So do you remember on your formula sheet for inductors specifically, you're given this equation. E to the negative t minus t naught over tau.
Yeah,
Remember this equation?
because you have to do the first, or, yeah, you have to do the two different
Mm-hmm.
times.
Time intervals.
Yeah.
Yeah, exactly. So essentially this equation comes up whenever you have a switching event that does not take place at t equals 0. So we were able to use this equation for our first IL of t equation because t naught here is just 0. So we just plugged in 0 for t naught in both positions, and we were able to solve like that. However, now we are looking for the circuit or the equation for the current through the inductor for t greater than 0.1 seconds because the switch now flipped to position C at 0.1 seconds. So we just have to keep that in mind, especially, for our exponential term. We need to make sure that we put negative t minus 0.1 over whatever our time constant is. You have to remember that. So first things first, let's draw our circuit in position C. All right, so this is kind of step 4 here. All right, resistor. Current source. All right, and we have 60, 20, 40, 20. 60, 20, 40, 20 amps, ohms, ohms, ohms. All right. Now, so this is where things get a little different. Now to find your initial condition, right? Because now we have to build our new equation. Usually the first step is to short out the inductor and solve for the current, and that's your initial condition, right? That can't be done here. When we short out the inductor, this current is your new IL of infinity for your second equation. In order to find your initial condition for your second equation, you have to use your first equation for IL of t. And let me see if I can explain that well, because it's kind of a complicated reason. So as you know, inductors, the currents cannot change instantaneously, right? So is it accurate to say this? The current through an inductor at 0.1 minus, as it approaches 0.1 from the left, is equal to IL 0.1 as right after 0.1 as t approaches 0.1 from the right. Right? We can say that those values are equal because it cannot change instantaneously. Even though the switch at 0.1 is shifting, the current through that inductor has to stay the same for that instant, right? So would you also agree with me when I say that this equation describes the current, or can describe the current, at t equals 0.1 minus? Yeah. This equation for IL of t encapsulates the current through the inductor for this time frame. And notice how I put less than or equals to. That's because whatever value we get for IL of 0.1 holds to be true at 0.1. It's inclusive of 0.1. So that's kind of the theory behind it. In simpler terms, whenever you have multiple switching events, you always use your first equation to find the initial condition of your second. Always. So that's exactly what we're going to do. IL of 0.1 is equal to 10 amps e to the negative 0.1 over 0.1, our time constant, which is just 10 e to the negative 1, which is going to be 3.689 amps. All right, I know that's kind of a lot. Any questions at all?
So that's going to be our current where IL is, like where would we put that after? That goes
Like where in the equation?
That goes where IL of infinity is.
That goes where for IL of t naught.
Okay.
The time of our switching event, IL is 0.1.
So now we just need to find IL.
Yes. Now we're going to look for this value, which is the steady state condition of the inductor for this circuit, and that gives us IL of infinity. So we short it, we solve the current.
Okay.
Yeah. Any other questions? Okay.
For the last one, like
Yeah.
you always short the inductor, or like to make it the wire.
Yes. I hesitate to say always because we're going to get into it. There's some edge cases you run into, specifically when an inductor is in parallel with a voltage source, where you cannot short it out because that creates problems. We'll get there, right? But as long as you don't have one of those weird situations going on, which most of the time you probably won't, yes, you do. You short it, you solve for IL infinity. Yeah, that's a good question. So, okay. We found our initial condition. Now, just one more time, just to kind of highlight the theory of what's going on here. This IL of 0.1 is the same current that's going through this inductor at t equals 0.1, and is also the same as the current going through this inductor at t equals 0.1. Even though they're completely different circuits, because the switch flips, the current is still the same. It cannot instantaneously change. And that also kind of really hammers down the point of me saying that even though we never reach zero, we still find IL of infinity to build that first equation that we built. I know I'm spinning back a little bit right there, but that's why we did it, right? The lowest that current is going to get is 3.689. Never gets to zero, but we're still going to find IL of infinity to model that equation. So anyways, I digress. So we found IL of 0.1. Now we find our IL of infinity. And let me do it like this. So 4, then 5. Step 5. Now we're finding IL of infinity. And let's simplify the circuit real quick. There's one thing we can do to make this a little bit easier.
Quick question.
Yeah.
I think you may have drawn that one a little wrong. Like the 20 is supposed to go down, and the
Oh, you're totally right. Yeah.
40 is on yours.
Yeah. Thank you. All right. It's right there. Yeah. Okay. Is that, wait, no, that's 20. 20 ohms. And that's 40 ohms. Okay. All right. Now,
And the 20 also goes down with the amps.
oh, yeah. Thank you so much. Yeah, because now that's going to become very relevant in solving for IL infinity. So, okay, one simplification we can do, right? Pretty obvious, I hope. Yeah, we get rid of that 60 ohm resistor. It's being shorted out, so it does not affect this circuit at all. We can get rid of it. Now, what would be the easiest way to solve for I love infinity here?
Why does the 60 ohm resistor get shorted out?
Yeah, so it's because it's being shorted, right? Definitionally, a component is getting shorted when the same node is on both sides of it. So if we highlight it, you see that this same yellow node is on both sides of it. Whenever that happens, you can get rid of the component.
So source transform.
Yeah, you could do source transformation. But that would require two equations to then solve for I of infinity. You do a current divider. Yeah. You just have to be a little bit careful with this current divider.
The other resistor.
It's the other resistor in the numerator, and there's some weird things going on with the sign here. So it is
You did a
opposite.
node voltage.
Yes. Yes. Yeah, if you made this your ground, you would just call this V1. V1 over 20 plus V1 over 40 plus 20 amps equals 0. Solve for V1, then say I of infinity is V1 over 20.
Okay.
Yeah, that works. Current divider is optimal if you're comfortable with it. If you're not, just do nodal. Never goes wrong. But current divider here would be I of infinity is equal to negative 20 amps times, like Liam said, the opposite resistor in the numerator over 40 plus 20 ohms, which gets us negative 13.3 repeating amps.
Wait, can you explain again why it's a negative 20?
Yeah, of course. So current divider, the way it works is you need a current source in parallel with two or more resistors. And there's two components of the current divider. There's your source current, and then there is your sort of your resistance ratio, right? That tells you how much current is going through each branch. Now for your source current, that's going to be the current source, right? Naturally. And that's going to be entering the junction like this. Now, if you don't include a negative sign, the current that we would have solved for is the one going in this direction. Likewise, if we were to solve for the current going through the middle branch and left it positive, we would be solving for the current going up. Because that's just how current divider works. You have your source current entering, and then the currents that you're solving for
Have to be leaving?
are leaving the junction that your source current is entering. So if you have a current that you're trying to solve for that is entering the same junction as your source current, you have to include a negative sign. Make sense? Cool. Okay. So that is going to be our final condition. Now we are going to solve for our second time constant. And the procedure here is pretty similar. Right? We remove the inductor, replace it with terminals, and solve for the equivalent resistance as seen by those two terminals, which is 60 ohms, 20 ohms, 40 ohms, right? 60, 20, 40, yep. All right, and we're gonna do our equivalent method because that's the easiest way to do this, so all the current sources turn into open circuits. That's why this is drawn as an open circuit here. And so just to simplify things a little bit, I'm going to remove that entirely. And hopefully it's pretty obvious what the equivalent resistance would be here.
30.
30, yeah. And let's go into a little bit as to why that is. So we can combine the 20 and the 40 ohm resistors in series, right? And so we're left with this. 20 plus 40 is also 60. And a quick little trick you can use is when you have two resistors in parallel with the same value, you can combine those resistors, and the equivalent resistance is just that number divided by 2. So you can then reduce that into a 30 ohm resistor, which is your new R Thevenin.
Why do we have like an open terminal like on the left of the 60 like where the inductor is?
Where the inductor was? Yeah, so when finding a time constant, what you're doing is you're finding the Thevenin resistance as seen by the inductor or the capacitor, in this case, inductor. So when you're finding R Thevenin as seen by a specific component, the procedure is you take that component, you remove it from the circuit, and you replace it with two terminals, like these. And you want to look for the equivalent resistance as seen by those two terminals. And when you're looking at resistances as seen by two terminals, there's some implications that come with that, right? Let's just look at this random circuit, for example. All right, I'm just drawing a random circuit here. Now, initially looking at this, right, these just look like open circuits. So you would be tempted to say that these two resistors are in series because these are open circuits. However, that is not the case. You're looking for the resistance as seen by these two terminals. So these two resistors are in series, and this resistor is in parallel with this series combinations. So a bit of a sidebar there, but what I'm trying to say is you just have to be careful when you're finding resistances as seen by terminals because they're not open circuits. So yeah, that's why we remove the inductor, replace it with terminals, and find the Thevenin resistance. And that's going to be 30 ohms. And so our new time constant is going to be L over R, which L stays the same, 6 henries. Our R is 30 ohms. So that's going to be 0.2 seconds. And so our new equation for IL of t is going to be IL of infinity, which is negative 13.3 repeating amps, plus, and then we have IL of t naught minus IL of infinity. All right, so t naught we found to be 3.689, and then minus negative 13, so plus 13.3. And that gives us 17.02 amps. E to the power of negative t minus t naught, t minus 0.1 over our time constant, 0.2 seconds. And that is our second equation for IL of t for t greater than or equal to 0.1. And now, last step. This problem's so fun, isn't it? Last step is to, of course, use IL to find I3. So I'm going to redraw the circuit. As such, and I'm only going to label one resistor here because only one resistor is relevant to us. So remember, this is the current IL of t, and this current is I3 of t. So again, this is circuits 2 territory right now, so bear with me here. I'm going to ask you a couple of questions that hopefully leads up to you intuitively being able to grasp what you're supposed to do here. So first things first, this inductor and this resistor, what sort of relationship are they in?
Parallel.
They're parallel, right? What does that mean about the voltages?
They share voltage.
They have the same voltage across them. They share a voltage. The same voltages across them. So would you agree with me when I say that if we were to find the voltage VL across this inductor, we could use that to then solve for I3? Because the voltages are the same. That's just a definition of circuits. Components in parallel have the same voltage across them. So if we can find the voltage across this inductor, we have the voltage across the 60 ohm resistor, and then we can use Ohm's law to solve for I3. Now the reason I'm talking about the voltage across the inductor is because we have everything we need to solve for it, using a very specific and key property of inductors. That is, VL is equal to L times the derivative of IL, dIL over dt. Which means that VL is equal to L, which is 6 henries, times the derivative of this expression. Okay, now this is something you can punch into your calculator, although the CAS doesn't like exponential functions that much. It like converts it to a decimal, which is really annoying. But you can still kind of do this semi-easily just using basic calculus, right? The derivative of a constant is 0, so the 13.3 is going to go to 0. And you can break this fraction up. This is how I think about it. You can break this fraction up into this e to the negative t over 0.2 plus 0.1 over 0.2. Right, I'm just breaking up that fraction there. And because we're going to have to use chain rule to find the derivative of your exponential function. And so when you do chain rule, I was trying to think of like the mathematical like way to, I don't freaking remember that. Essentially it's this. You're going to be left with negative 1 over 0.2 times 17.02, that stays there, times the derivative of an exponent is the same exponent, t minus 0.1 over 0.2. So all I did there is I took this relationship, L dIL over dt, and so I plugged in L, and then I took the derivative of IL of t. So this went to 0. We keep the 17.02 in there, and we take the derivative of the exponent of the exponential, and the derivative of this is negative 1 over 0.2. Again, your calculator can do this, so try not to get too bogged down in the weeds of that. But yeah, that's what you're left with. And so you get 6 times, what is that, negative 5 times 17.02. And you'll get negative 510.6 volts e to the negative t minus 0.1 over 0.2. And remember, by Ohm's law, we're looking for I3 of t is just going to be VL over 60 ohms. So we just take 510 and divide it by 60. And we get negative 8.51 amps e to the negative t minus 0.1 seconds over 0.2 seconds. And that is for t greater than, or just greater than 0.1 seconds. very long problem. But we got it right, so that's cool.